So let's talk about what accuracy and precision is. There's a lot to unpack in all of this. Now, when you're measuring something, it is not exactly perfect. There is a bit of an error to it. So in Edexcel, what they use is something known as the uncertainty approach to measurement. This means that the measurement is treated as an interval of reasonable possible values. Now, what that basically means, if I have a value of 25.4, and this is in centimeters, what a physicist might do, okay, is do plus or minus 0.1 centimeters. This is just the error bound. Maybe you've heard about it in math, but basically the value could be anywhere between 25.3 and 25.5. You either add the 0.1 or you minus the 0.1, and that gives you the interval. So anything between that is good. Anything like beyond that or under that, not so good. So why are the readings not exact? And one reason is limited resolution in instruments. You know, rulers, you could go up by, I think, 0.1 centimeters because you got a 1 centimeters and then you got a division of 10. So it's like 0.1. So what happens if it's like slightly between them? Another one is the fluctuations of the quantity you're measuring. So let's say I'm trying to measure the wind speed. Wind speed isn't always going to be the same. It is going to vary. What you do in this circumstance is you'll take a different amount of readings and then you'll just take an average of what the wind speed is. Another thing is changes in the environmental conditions. So let's say I've got a piece of metal, okay, and I heat up the piece of, not I heat up, but it's a hot day. And on a hot day, the metal atoms, let's do some physics, they vibrate more because they got more temperature and they expand, okay? So there will be a difference in the measurement of the piece of metal on a cold day and the hot day. Also, the difficulty judging the exact position of an object. If you look at water, what happens with water, it usually curves upwards. So it goes from the top over there and goes down. It's kind of like water isn't this kind of like flat surface. It's like a bit up there. And sometimes what you're figuring out is where do you measure the water from? Do you measure it from where it hits the sides, where it's the highest, or do you measure it when it dips down at the lowest point? Also, the calibration could be imperfect. So, for example, if you buy a measuring tape, a cheap one, because of the manufacturing defect, sometimes the kind of like calibration, the markings, they're not exact. So, like one line could be closely together, and one line could be far apart. Is imperfect. So we call it imperfect calibration. There's sometimes zero errors. If you've ever gone to on one of your scales, actually it shows like 0.2 kilograms and there's nothing on the scales. That is an example of a zero error. And there is parallax errors. Also, parallax errors is like when you look at something and you look at it from the side, you look at it, you're seeing different kind of angles to it. So I will describe a parallax error. If I'm looking at it from this angle right over there, I'll actually see it a little bit lower. So I'll see the value a little bit lower because I'm looking from the above. If I'm if I'm looking from here, okay, I would see it a bit higher than it should be. If I'm looking at it from there, I would see it more exact to what it should be. So every angle I look at will give me a different kind of reading. That's what we call a parallax error. And also there's a limitations in the experimental method. So if you've ever done an experiment and it's done in a vacuum, why is it done in a vacuum? That's to remove the air resistance. So if I drop a ball and I'm just measuring the time, I'm assuming there's no air resistance, but in reality, there is a bit of air resistance. But our method actually ignores the air resistance. Also, there's the reaction time. Okay, so if I'm doing a stopwatch and I'm measuring someone, there I could see that the person crosses over there, but it takes me a while to just like hit the thing because I have to send a message from my brain all the way up to my muscles to contract. Hey, some biology here, and squeeze the actual stopwatch. So there's going to be an error in that also. So there is something known as the true value. The true value is the value that will be obtained from a perfect ideal experiment. Now, it's very nearly impossible to get that because every instrument has limitations. The environment cannot be controlled perfectly. The quantity may vary slightly, and repeated measurements are never going to be infinitely precise. So in their Pearson Edexcel, they say that the true value is the value that will be obtained from an ideal experiment. So now let's look at what an error actually is. So an error is, for example, the measured value minus the true value. So let's say I measured something and it is 52.6, but the accepted true value is 52.9. That means I've got an error of 0.3 grams. That means that the true value is minus 0.3. The measured value, is 0.3 under what it should truly be, the accepted value, you could say. Now, an error isn't necessarily a mistake. It could be unavoidable random variation, a systematic effect. We talked about this before. So what is an example of an actual mistake? An actual mistake is, let's say I measured 1.26, yeah, and I write down the value of 1.62. So I got those two mixed up. That is actually a mistake. Another mistake is forgetting to convert centimeters into meters, using the wrong equation, reading the wrong scale, copying the calculator value incorrectly, recording the time against the wrong distance, and X, Y, Z. So let's now talk about uncertainty. So an uncertainty describes the interval within the true value can be reasonably considered to lie between. So X is equal to X measured, delta X. Now X measured is the measured value, and this is the actual uncertainty. So if I had 18.6 plus or minus 0.2 centimeters, as we did it before, we'll add the 0.2 and minus the 0.2. So the distance will be between those two values. So what can affect that uncertainty is the measurement instrument. So a ruler has a bit of an uncertainty. That's why we try and use the most precise instruments. Also, a spread of the repeated readings, which means if you measure the exact same thing, maybe 5 times, for example, you'll often get 5 slightly different numbers. What we often do is we'll look at the range. So we'll look at the smallest number and we'll look at the highest number, or we could do standard deviation. I'm not going to get into it too much, but then it will give us a uncertainty. Also, the experimental method, sometimes the uncertainty doesn't come from the tool, but physical realities from how you do it. So for example, the temperature of the hot liquid, and we're trying to measure how the temperature from the hot liquid changes over time to become a cold liquid, but we do put no lid. And if we put no lid, the heat comes out. Sometimes there's a random error. So for example, temperature fluctuations in the environment, vibrations, maybe there's a problem with the human reaction time or XYZ. And also there's something called a systematic error. Now, a systematic effects push your data in one direction only. So either it makes it too high or consistently too low. So, for example, 0 errors. If I don't go on the scale and it shows plus 0.2 kilograms, that means all of my readings are going to be slightly high because they'll always have 0.2 kilograms extra max error. If I'm always looking at it from this direction, then my reading's always going to be slightly lower than it actually should be. So if I'm doing it 5 times in a row and I'm always looking at it from that thing, I'm going to repeat the error and it's always going to be slightly low. So it could always go slightly high, slightly low, but it's repeated. Or something wrong with the actual badly calibrated scale or things like that. So let's look at the difference between uncertainty and error. So when we talk about error, it is about reality, and uncertainty is more about confidence. So error is how far away you are from the exact from the true value. The uncertainty is you got two kind of values. It could be between here and it could be between here, and it's somewhere there. I just don't know where exactly. So let's say a student actually records something 2.04 seconds, plus or minus 0.06 seconds. So this is our uncertainty. It could be plus 0.06 or minus 0.06. But let's say the true value, the accepted value is 2 seconds. So what we have to do is we have to do the measured value, 2.04, minus the true value, 2, and we know we're 0.04 seconds off. Now, to calculate the uncertainty, you don't need to know the true value. You just need to look at your stopwatch, and if your stopwatch has a resolution of 0.01 seconds, you know it could be slightly above, slightly below, and you also add your reaction time. And adding all of that maybe gives you an uncertainty of 0.06. Now, you do not know the error unless you are given the true value. Maybe you get it from a textbook or something like that. So the golden rule is you can have a measurement with an unknown error, but you can always calculate your uncertainty because your uncertainty does not depend on the true value. So if I took a kind of like a bullseye where you shoot the bullseye over there, the bullseye, let's say that is the true value. And where your arrow hits, let's say your arrow hits there, that's your measured value. And the error is the distance between the two of those. But the uncertainty is where exactly did you hit. You don't know exactly where you hit. You kind of got a blurry image, but you know you hit somewhere on the right. You just don't know exactly, but you know it's between these two values. So let's talk about accuracy. A measurement is considered accurate if it's judged to be close to the true or accepted value. Accuracy is affected by random errors and systematic errors. So a systematic error is basically the enemy of accuracy. They occur when the fundamental flaw in your tool, like your equipment or thing, so it's badly calibrated, like it's always 0.3 kilograms more or something like that. So basically, you could have a very good accuracy, but if you like shoot an arrow and they multiple times and they all land within the same location, so they could all land over here. They're all grouped together, but they're always going to be far from the true actual value. The true value is in the bullseye, right? But your values are always hitting that. They're always going to be slightly off, right? You could say 0.3 centimeters off in that direction. So in this case, taking more measurements doesn't help. If your scale is always 0.3 centimeters that or 0.3 grams or what X, Y, Z. Because you're always going to have an average that is a bit too far from the true value. When we talk about random errors, they are unpredictable. So, you know, the wind could be slightly low, slightly high. You don't know where it's going to be more scattered because you don't know the temperature fluctuations, hot, cold, like it's just random. So like if I'm shooting an arrow and my hands are shaking, all right, I don't know exactly where my hand's shaking. It shakes a bit there, shakes a bit there, but I'm not going to be hitting the center that often. So I'll be firing something like there. Maybe some will hit the center, but like it'll be scattered. But unlike systematic errors, if you keep on repeating it, you're going to like sometimes you're going to hit the outer parts, but you're going to hit the center a lot of the times. So you get close to the true value. Let's say that the accepted acceleration, okay, the true value of acceleration is 2.5 meters per second squared. And a student actually measures the acceleration and they get 2.47 meters, and their uncertainty is plus or minus 0.08 meters per second squared. So if we minus the 0.08, we get this. If we add the 0.08, we get that. And we can see that the 2.5 actually lands between both of them. So we can say that it is accurate. Now, when we're talking about precision, this is basically how the closeness of the repeated measurement. So as we can see, the spread of these are relatively small. We could take the highest value, we could take the smallest value, we can minus the 2, and the spread is 0.02. But if we look at something else, like this, we could see the difference between the highest value and the smallest value is 0.9. There's a much bigger spread. So when we talk about accuracy, we're talking about, are the measurements close to where they should be? When we're talking about precision, are the repeated measurements close to one another? So let's go through some kind of examples. So let's say we have a bullseye over there, and we get readings that are scattered all over. This is not precise. This is not accurately because they are widely scattered. They're not centered around the bullseye, which is the accepted value. And they're kind of inconsistent with one another. They're not grouped together. They're all scattered about and far away from the true value. So this suggests that there's a lot. If we had a bullseye over there, but we got our readings were all over here, this is precise because they're all grouped together, but this is accurate because they are far away from the actual bullseye. This is a typical systematic error, a zero error. So for example, your calibration might be 0.1 centimeters too high, 0.1 centimeters too low, even at the zero mark, or like I use that scale. When there's nothing on the scale, you're showing minus 0.2 kilograms or plus 0.2 kilograms, something like that. Another one is you got a center over there. You got a few points that are like so. You got some that are all the way. So this is not precise, but it is accurate on average because some of them are close to the center. So this suggests that there are large random errors. That's why they're scattered all over. There's poor precision. They're not grouped together, but a mean that is close to the true value. And then here you got the bullseye. Let's write the bullseye. And then you got values all over here, some landing in the center. This shows high precision. They're all grouped together. High accuracy because they're all close to the bullseye. So there's a little random error. There's little systematic error. So what are some examples of random errors? Variation in the human reaction time, fluctuating electrical signals, changing air currents, wind speeds, small changes in temperature, inconsistency when releasing the object. So sometimes if you're dropping a ball, you sometimes drop it like that. Sometimes you just drop it like that, like inconsistent. The vibration of the apparatus could like change the readings. So random errors increase the spread of them. They make it less precise and they scatter it, the readings all. So ways to reduce the random errors: repeating the measurements, calculating the mean, using the line of best fit, measuring over a large distance, because over a large distance, the errors, the random errors become less significant. Measuring over a long period of time, the same kind of reason. Using automated sensors, which are more accurate. So if we were looking at reaction time, let's say our reaction time is plus or minus 0.15 seconds, and the measured time is 0.6. Okay, so the uncertainty would be 0.15 because that's the uncertainty divided by the measured, times that by 100, and we get a 25% uncertainty. Whereas if we did it instead of 0.6 seconds, we did it over a period of 6 seconds, and we times this by 100, we get 2.5% uncertainty. So we drop the uncertainty by making it much larger. Systematic errors are when the readings are too high or too low, and they're shifted by a constant amount. And systematic errors reduce the accuracy because they're far apart from what the true value is meant to be. They still could be precise. I mean, you could still get them fairly like all clumping up together over there, but they're far away from the true value. So how do you reduce the systematic errors? You check the equipment measurements, the zero errors before doing any measurements. Another one is using the correct reference point. So if you got a ruler, sometimes people will measure from there, but if the zero starts from here, you're meant to measure it from there. So you're going to be slightly off always. Compare the results with a second instrument. If they're both given different errors, then you know it's going to be a systematic error. Use a control experiment. So for example, if you're testing how much a specific chemical speeds up the rusting process in water, you must run a control where it's just with the water and the metal and no chemicals inside it. And this is the baseline. So if the control rusts faster than expected, you know something else is in the room, such as a high humidity, temperature, or something like that. Also, reducing the heat loss from with using insulation. So if you're heating up something, you want to minimize the heat loss, put a lid, wrap it around and things like that. Now let's look at, so we got a line of best fit, and we got some readings that are like over here, but some of them are random, some of them are too high, too low, X, Y, Z. So they got a random and a systematic error. So they are far from the expected line. So there's some evidence of random error because they're slightly high, slightly low, and there's some evidence of systematic because some of them are always like that or always up like so. And then you got systematic error. So for example, if there's a high precision, but they're always like slightly above the line or X, Y, Z. Reality, the line of best fit will go like that, but you kind of get the drift. And then you got the random error where they are just like, some are slightly high, some are slightly low, X, Y, Z. Some of them are like down here. So there's no obvious systematic because some of them are like either close, far, is all over the place. And then you got when you start from the origin over there, and you got all of the points kind of like lining up perfectly like so. So like compared to the systematic where it starts over here and goes up, where you got slightly above, this one starts at the origin and it goes like so. Now, you're not always going to start with the origin, but it kind of explains it a bit. So random errors are when there's roughly balanced number of above and below it, and there's a overall trend. So there's no attempt to pass through every point. But systematic errors are indicated when the line is expected to pass through the origin. So if you expect it to go through here, but instead it starts over there and you got the points all over here, you know this is a systematic error. So when we talk about resolution, this is the smallest measuring interval or that can be distinguished. So with a meter rule, the typical resolution is 1 millimeter. With calipers, it's 0.1 millimeters. Digital stopwatches is 0.01 seconds. It will measure it to that calibration. High resolution does not guarantee high accuracy or high precision or correct calibration. So, for example, you could have something that is got a good resolution to 0.01 seconds, like so, right? They got all 0.01 seconds, but they're all very far off. Some is 1.5, some of them is 1.2. So they're not precise, but they have high resolution. Let's say we measured something and it's 1.8 millimeters, okay? But when it's on the zero, it gives us a plus 0.04 millimeters, okay? When fully closed, okay? It's like a caliper. I'm not going to get through it, but it gives us a 0.04 when it should be actually a 0. So the correct reading is this is too high, so we're going to minus it. And we get 1.82 millimeters. And then there is a negative 0, okay? Where instead of plus, it's minus 0.03 millimeters. So if we measured something 2.15 millimeters, we know it's slightly lower than it should be. So we do 2.15 minus the minus reading. So this turns into a plus and we get 2.18 millimeters. And that is the corrected. So we could use this equation. The zero reading is basically this, what we look at when we got the zero. Now, for Pearson and Excel, the uncertainty guidance give using half the smallest scale interval. So let's say we use a meter rule, okay, and it has it's in the 1 millimeter resolution. We divide it by 2, we get 0.5 millimeters. Let's look at an ammeter. If it's got a resolution of 0.1 amps, we divide it by 2, and this will be our uncertainty. Now, if we have 2 readings, okay, let's say a meter rule, and we use the meter rule twice, we have to add this uncertainty twice because we're using the meter rule twice. So the uncertainty would become 1 millimeter plus or minus. So when repeated readings differ, the uncertainty can be used, you can get it from the half the range. So half the range is the maximum value minus the minimum divided by 2, okay? So if I have those readings, I could add them all up, divide by 5 to work out the mean. So the mean would be 8.44 millimeters, sorry. And then the range. So the range will be the highest value minus the smallest value, 8.39. And that gets me to 0.07. I didn't just have to divide it. So I use this formula to work out what the uncertainty is going to be, which is 0.035 millimeters. Now, if I round this to 3 significant figures, I get 8.42, and I have to round this to 3 significant figures. So round it up, it's 0.04. So this is the answer. Now, repeatability is basically, can I do this again right now and get the same answer? So to test repeatability, you must keep absolutely everything the same. So the same person who's doing it, the same reaction time, same method, same apparatus, same time. Because the same time, there could be different temperature in the room, different humidity. So repeatability proves that you have successfully eliminated the massive random errors. If your measurements are all over the place when you try and repeat it yourself, it means your hands are too shaky, the tool is broken, or your method is completely Now, when we talk about reproducibility, can someone else somewhere else do this and get the same answer? Where they use different people, different instruments, different environments, and sometimes different methods. So reproducibility just proves that your results are due to nature and not just like something due to your specific setup. Now, reproducibility is very hard to achieve if you have any systematic errors. So if someone else repeated it elsewhere and they used a tool that didn't have a systematic error and yours did, your test will basically fail the reproducibility test. Now, something is said to be valid if it measures the quantity it's intended to measure. A method may produce precise results, which are all clumped up together, but far away from the actual true value. For validity, you're aiming for the correct target. You're not trying to just get like precise results, trying to get to the center of the true value. So no random errors. You want it to be reproducibility, no systematic errors, and validity. So what are some common examination mistakes? Some people will say the results are accurate because they're close together. That's not the case. If they're close together, you're saying that they are precise. Another mistake will be saying repeating removes systematic errors. It doesn't repeat. Systematic errors is where you consistently get a bit off. They'll be precise. They could be precise, but they'll be a bit off the true actual value. So repeating and calculating the mean reduces the effects of random variation, not systematic error. You can't just say use a more accurate equipment. You have to say, for example, use a light gate. We'll go through a light gate later. Electronic timer instead of a stopwatch. You can't just say human error caused the result. You have to say variation in the reaction time. So the operator's reaction time caused the random uncertainty in the measured time. You can't just say the stopwatch is accurate to 0.01 seconds. You have to say the stopwatch has a resolution of 0.1 second. You can't just say accuracy is 4%. You should say the percentage difference from the accepted value is 4%. So let's go through again. Precision is the repeated measurements have a small range and therefore high precision. Accuracy is the accepted value lies within the uncertainty interval. So the result is consistent with the accepted value. Hopefully you found this video helpful. Long topic to go through. Take care and have a nice day.